Good day to Madam Sharina. Today we will dive into the analysis of the iron-carbon binary system, a fundamental topic in this subject. We, representing the party, and before we begin, let me introduce our team members. Our team members has three, which is me, Alicia, Amanda, and Charlotte. And let's begin.
Let's start with the overview outline in our tables of content. First, we will introduce the topic and its relevance in material science and engineering. Then, we will move into task 1, which include two subtopics, which is the engineering applications and iron-carbon analysis, delving into the structure and the significance of cementite. Following this, task 2 explore the lever rule analysis, essential for understanding phase proportions in the iron-carbon diagram. After that, we will proceed with a discussions of the finding, followed by a concise conclusions summarizing the key insight. Finally, we will share the reference that support this study. On the right, you will see the iron-carbon phase diagram, a critical visual for this topic, which we will revisit as we progress. Let's dive in. Let's start with the overview outline in our tables of content.
For the introduction slide, we take a closer look at iron-carbon, specifically iron carbide, which is also referred to as cementite and has the chemical formula Fe3C. Iron carbide is classified as an intermediate transition metal carbide. It's made up of 93.3% of iron and 6.67% of carbon by weight, and this unique composition contributes to its significant properties. One notable characteristic of cementite is its orthorhombic crystal structure, which plays a key role in its steels, which are critical materials in constructions and manufacturing industries. And the diagram, also microstructures shown here, illustrate that the phase relationships and properties of iron-carbon alloys, emphasizing the importance of cementite to metallurgical application. Next, in this slide, it focuses on three major engineering applications of iron-carbon, which is alloying, heat treatment, and wastewater remediation. Let's explore each one in depth. The first one is alloying, which involves adding elements to iron-carbon alloys to create materials with a specific properties. For example, low carbon steels are used in automotive panels due to their ductility and malleability. Second is high carbon steels are ideal for cutting tools and springs, known for their hardness and wear resistance. And the third one is gas irons used in engine blocks and machinery provide high comprehensive strength. And at the normal temperatures, these alloys consist of ferrite and cementite phases. However, alloying comes with its own engineering challenges, such as alloy separation during cooling, and which can affect material uniformity. And the second is balancing cost efficiency while producing high-performance alloys. The second one is heat treatment. It is the process of heating and cooling iron-carbon alloys to modify the microstructures of alloys to achieve desired mechanical properties. The key processes include annealing, which refines grain structure, reduces hardness, and improves ductility. The second one is normalizing, which creates uniform grain structures and moderate hardness. And the third one is quenching and tempering, which hardens the steel and then temper it for a balance of strength and toughness. But there are challenges here as well, which is managing thermal stresses to prevent cracking during the process and ensuring uniform properties in larger components, which can be tricky to achieve. And the third one is wastewater remediation. One of it known as iron-carbon microelectrolysis, and this process leverages iron-carbon alloys to remove pollutants from water. The applications include removing organic contaminants such as azotides and pharmaceutical residues. The second one is precipitating heavy metals such as chromium, and lead through the redox reactions. And the third one is reducing chemical oxygen demand, COD, and biological oxygen demand, BOD, enhancing our water quality. However, there are engineering challenges to consider, such as managing sludge production and ensuring the long-term effectiveness of the process. In summary, these applications showcase the versatility of iron-carbon alloys across multiple industries, from manufacturing to environmental solutions.
In this slide, we focus on task 1.b, iron-carbon analysis, which estimate the iron-carbon system. Why we choose this element is because this system is critical for the steel productions and industrial processes because it demonstrates the formations of diverse phases and microstructure. It also serves as a practical framework for understanding phase equilibrium, which is essential in material engineering. The component of this system is iron and carbon, which combine to form various phases. The key phase fields include ferrite, which is low in carbon and form at lower temperature, and austenite, which form at intermediate carbon level and higher temperature. Cementite is hard and brittle phase is found at the far right side of the diagram. Additionally, phase combinations such as ferrite and cementite lead to pearlite formations, while austenite and cementite occur at intermediate carbon during the cooling. The iron-carbon phase diagram shown on the slide illustrates the relationship between temperature, carbon, content, and phase transition. This analysis is essential for optimizing the material properties and understanding the behavior of steel under the various conditions. Let us now proceed to the next section. In this slide, we focus on task 1.b, iron. This slide delves deeper into task 1.b by discussing the influence of the temperature on the compositions and pressure of the iron-carbon system. First, let's consider the influence of temperature on the compositions. At high temperature, austenite is favored, allowing more carbon to dissolve into the structure. Conversely, at low temperature, ferrite form, which hold less carbon. Cooling processes lead to significant phase changes such as the formations of solid structure or combinations like austenite and cementite. At the eutectic point, which occur at 4.3 weight% carbon and 1147 Celsius, the liquid transforms into the mixture of the austenite and cementite. Now, for the influence of temperature on pressure. Higher pressure stabilizes austenite and cementite phases, increasing the melting point of the alloy. Additionally, changes in pressure can shift the liquid and solidus line, thereby affecting the cooling and solidification rate. In industrial processes, temperature remains the primary control factor, with pressure adjustment playing the secondary but crucial role in specialized applications. This understanding helps optimize material properties and industrial performance.
Next, I will focus on the level rule analysis in the context of the iron-carbon binary system. We will explore the principles behind the level rule, its application, and the implications of accurate data interpretation. To begin, let's discuss the level rule and its significance. The level rule is a fundamental tool used to determine the relative amounts of coexisting phases in a two-phase system at equilibrium. This is particularly important in analyzing phase transitions and understanding material behavior under varying conditions, such as temperature or pressure. The level rule can be mathematically expressed as follows. WL represents the weight fraction of the liquid phase, W alpha represents the weight fraction of the solid phase, Cl denotes the carbon composition of the liquid phase, C alpha is the carbon composition of the solid phase, and C naught is the overall composition. This formula allows us to derive the weight fractions of each phase. In our analysis of the iron-carbon phase diagram, we identified two phases at equilibrium, the liquid phase and the solid phase. We located the tie line at the specific temperature, which provided us with the following compositions: Cl equals 4.2% and C alpha equals 0.02%. For analysis, we initially assumed C naught to be 3.5%. Based on the assumed C naught value of 3.5%, we calculated the weight fractions of the phases. The results indicated that WL, the weight fraction of the liquid phase, is approximately 81.31%, while W alpha, the weight fraction of the solid phase, is 18.69%. However, this approximation may not reflect the actual scenario accurately. The initial analysis, which used an assumed overall composition C naught of 3.5%, calculated weight fractions of 81.31% for the liquid phase and 18.69% for the solid phase. However, a closer examination of the iron-carbon phase diagram revealed that the actual overall composition C naught is 2.14%. This discrepancy highlights how approximation, which often employed for simplicity in calculations, can introduce significant deviations from reality. The overestimation of the liquid phase and the underestimation of the solid phase proportions demonstrate how small inaccuracies in input values can lead to large errors in interpreting phase equilibrium. In industrial applications such as alloy design, casting, or heat treatment, accurate phase proportions are critical for predicting material behavior, ensuring the desired mechanical properties, and avoiding costly errors. Although approximations may be useful for conceptual understanding or grid estimates, they fail to meet the precision required for practical applications, which reliability is paramount. This analysis underscores the need for meticulous data interpretation when using the level rule, as accurate inputs ensure consistent results and more effective metallurgical process optimization. Upon utilizing the correct overall composition of C naught at 2.14%, we recalculated our weight fractions. The new results revealed that WL is 49.53% for the liquid phase and W alpha is 50.47% for the solid phase. This correction demonstrates the critical importance of accurate data in achieving reliable results. Comparing the results, we see a significant difference between our initial and corrected calculations. The previous results suggested a liquid phase weight fraction of 81.31% compared to the corrected value of 49.53%. This stark contrast emphasizes how even small errors in input values can drastically alter phase proportions and lead to flawed predictions in metallurgical processes. Hence, the level rule is an essential analytical tool in the field of material science, particularly for the iron-carbon binary system. Our analysis underscores the importance of precision in data interpretation to ensure accurate predictions in practical applications, such as casting and heat treatment.
Now, let's explore the microstructures of this hypolytic alloy and how it evolves during cooling. The first one is solidification. The process begins as the alloy cools. Austenite starts to form as the permanent solid phase from the liquid. During this stage, the composition of the remaining liquid shifts along the liquidus line, approaching the composition of liquid of the carbon, which is 4.3%. At the same time, the composition of the solidifying austenite follows the solidus line, starting with the composition of the solidus, which is 0.02% of carbon. This marks the beginning of the microstructure's development. Next, the second one. Once the remaining liquid reaches the composition of the carbon liquid, which is 4.3%, it undergoes a eutectic reaction at 1147 degrees Celsius, which is the liquid goes into austenite plus with cementite. This reaction produces a eutectic microstructures called ladybirite, which consists of alternating layers of the austenite and cementite. And the final microstructures of the hypolytic alloy consists of two main components, which is primary austenite, formed during the early stages of solidification, and the second one is eutectic mixture, which is ladybirite, a combination of the austenite and cementite created from the remaining liquid during the eutectic reaction. And these microstructures plays a crucial role in determining the mechanical properties of the alloy. Understanding its formation is essential for tailoring materials for specific applications.
For the conclusions, ion-carbon binary system is fundamental aspect of material science, known for its versatility and critical role in various industries. It is well-defined phase diagrams allow engineers to precisely tailor the properties of ion-carbon alloy, such as steel and cast iron, to meet the specific needs. A key focus is on the critical transformations like the eutectoid and eutectic reactions, as well as the role of ferrite, austenite, and cementite. This transformation dictate the important mechanical properties such as ductility, toughness, hardness, and wear resistance. Also ultimately impact the alloy performance in the real-world applications. The Revel rule is essential tool here, offering a way to quantitatively analyze the phase proportions. This analysis helps us to understand how changes in a carbon content and temperature will influence into the material behavior. This knowledge is especially crucial in optimizing the heat treatment processes in a develop of alloy for applications like construction, automotive, and heavy machinery. Also in engineering applications such as alloying, heat treatment, and wastewater remediation. In conclusions, the ion-carbon system demonstrates how carefully controlling compositions, temperature, and microstructure can yield to a wide range of desirable mechanical properties. It highlights the importance of material science in advancing the engineering solutions and tracking the practical challenges.
These are the list of the references of the sources and literature review that we use in this analysis. And that's all from us. Thank you.